Hello, everybody. Welcome to the SETI seminar. Today, I'm particularly interested in this talk because there's new physics to be had in the realm of the humanly directly perceptible. And Mark's going to talk about this. As we know, general relativity is spectacularly successful from the Big Bang to like Jupiter, maybe closer. And quantum mechanics has been spectacularly successful from the level of string or M theory up to Bose-Einstein condensates. But they don't talk to each other. And nobody, really understands that. There's lots of theories and stuff. But why aren't these two very successful foundations of physics really in touch with each other or seem to be incompatible? So it's a really exciting place to work, is right here. And this is one of the places Mark works, in the realm of quantum mechanics and GR. So Mark is a professor of physics and applied physics at Stanford University. He received his BA in physics from Dartmouth and then a BA in physics and philosophy from Oxford as a Rhodes Scholar. And his PhD he got in applied physics from Stanford University. He joined the Stanford physics faculty in 1992, and then from 1997 to 2002, he was a member of the Yale physics department. He returned to Stanford in 2002. His current research interests are centered on the development of quantum sensors of rotation and acceleration based on cold atoms, application of these sensors to tests of general relativity, investigation of many-bodied quantum effects in Bose condensed vapors, investigation of quantum-enhanced imaging and measurement methods, and the investigation of ultra-fast laser-induced phenomena. He is co-founder of AOSense in 2004 and serves as the company's consulting chief scientist. So please welcome Mark.
Good afternoon. Thanks for coming. So I'm going to tell you about some experimental work at Stanford University where we're trying to understand in the laboratory what the limits of quantum theory are. What kind of parameter regimes can we describe quantum mechanics as being true in, and where might it fail? So I am from Stanford University and in the departments of physics and applied physics, and I'm going to describe to you the work of my research group, and some collaborations with the theorists also at Stanford. I want to start out with an experiment that happened in Germany in 1991 in the group of Jürgen Winnick. He did the Young's double slit experiment, not with light, but with metastable helium atoms. And this is how it worked. He had a source of helium. This helium beam illuminated a first slit. And back in the day, this was a microfabricated, about 100 micron wide slit that gave rise to a spray of helium atoms. But due to the laws of quantum mechanics, the Schrödinger equation, you would describe that spray of helium atoms as a cylindrically propagating set of wavefronts via the Broglie's principle. And these wavefronts were made to illuminate two more slits, which gave rise to two more wavefronts that then overlapped at a detection screen. Now, because quantum mechanics teaches us that these atoms have a characteristic wavelength, Planck's constant divided by their momentum, by analogy with what happens with optical fields, you expect to see interference of the atom de Broglie waves. And that interference was registered by this detector, which was scanned across the interfering wavefronts at this position. Now, how do de Broglie wavefronts interfere? Well, we're talking about manipulating the wave function of a helium atom, and the wave function is a mathematical representation for the probability of finding the atom in a certain position. So if I have wavefronts interfering, what I expect to see is a change in the probability spatially of detecting a helium atom. And so what they did was they scanned the position of this helium atom detector and looked for the probability of finding a helium atom at that location. So let's go to some data. Here is the position of that detector, and here is the number of atoms detected, and this is in counts per 5 minutes, and you see this oscillation, which if you've done the Young's double slit experiment with light in, say, an undergraduate physics lab, you would recognize that pattern shape. And basically, we can easily predict the shape of this interference pattern just from a basic wave interference phenomena, where in this case, you insert the wavelength of the helium atom as a Planck's constant divided by its momentum. So this kind of opened the field of de Broglie wave atom interferometry in the early 90s. And it was significant not because it showed us that Schrodinger equation worked, because we kind of knew that from the beginning of the 20th century, but there were some notable physicists in kind of like the 1950s, 1960s that said, yeah, we're good to go with Schrodinger equation, and we see all sorts of evidence for quantum interference of matter, Davis and Germer experiment, structure of the atom, and so forth. But you're never going to be able to build a de Broglie wave interferometer for an atom because, hey, whenever you build an interferometer, you need to make sure the relative paths of your two interfering beams are stable with respect to one another. And in the case of atoms, it's just not going to be possible to stabilize that relative path, so you see a well-defined phase in the fringe. And kind of by inference, what these naysayers were saying is that instead of seeing a stable fringe, that fringe would shake back and forth so quickly that you would never reflect or register the interference. And that was probably true in the 50s and 60s. We didn't know how to build, 1950s and 60s, we didn't know how to build apparatus that was that stable. But kind of when you got to the early 90s, microfabrication techniques had improved to the extent that you could make these small slits. We had enough control over how to build atomic beams and so forth that you could actually realize this textbook interference for atoms. So that was back in 1991, and the field has been vigorous since then. It's about 25 years from then. And you could ask the question, well, where are we today? So I want to show you some data that's out of my group in the last 6 months, where I have a picture here of, this is a picture in the sense that we've done some image processing. Everything looks better in false colors, my colleagues say. So what I have here is one clump of atoms and another clump of atoms. These are rubidium-87 atoms, and in each one of those clumps, there's about 10 to the 5 to 10 to the 6 atoms, almost 1 million atoms. And those two clumps are separated by 54 centimeters. I'll show you the apparatus in just a moment. And what's amazing about these two clusters of atoms is that each atom that's in these clusters is actually in two places at once. The correct quantum mechanical description of the photo I'm showing you, if I didn't take a photograph of it and record what was there, but instead I just left those atoms be, is that each atom is in a coherent superposition of that location and that location. And I have 10 to the 5 to 10 to the 6 atoms, each and every one of them in both places at once. So those are kind of words that we've uttered in the community of quantum mechanics over the past century, and we become, as physicists, scientists, comfortable saying saying things like that. When I say two things at once, places at once, think of yourself being in that chair and that chair simultaneously, both places at once. And according to quantum mechanics, if I looked and tried to check out where you were, then your wave function would collapse and you'd be either in that chair or that chair. So there's this whole aspect about how you observe the wave function and what constitutes a measurement. So this was actually a series of pictures stitched together, and we were definitely observing the wave function. After this picture was taken, the wave function was collapsed to that position or to that position. Now, what I'm going to show you with data in just a moment is what happens when we don't take the picture, and instead we bring those two ensembles back together. Now, if they're behaving quantum mechanically, what I expect to happen is I expect the wave functions of those ensembles to interfere like waves. And by virtue of observing this interference, that supports my inference that the only way I could have seen those interferences is if these two waves had been in two positions at once. And the atoms which were making up these waves, each atom was in both positions at once. So let me show you the apparatus, and then I'll show you some more data that supports that assertion. This is in the basement of the Variant Physics building at Stanford. And I inherited this lab when I moved back to Stanford in 2002. It's a marvelous lab that was built for some early studies with low magnetic fields. And so what they did was they dug a pit 10 meters down in the floor of the basement of the building. 10 meters down, I look down this tube, and there's nothing there but concrete on the walls. And what we did was we filled that tube with an ultra-high vacuum system that goes down those 10 meters. Here's, everything looks better in CAD, so here's the CAD drawing of that. And at the very bottom of that tube, we have a source of rubidium atoms. That's on this CAD drawing, it's here, and on this picture it's there. And if I take a camera downstairs and look, that's where that atom source is. And sort of using modern atomic physics techniques, we are able to do the following thing. We're able to collect rubidium atoms from a vapor source. We cool them with laser light. Stephen Chu, my colleague at Stanford, received the Nobel Prize in the late 90s for figuring out how to do that. We cool them down to temperatures of microkelvins, which, what does a microkelvin for a rubidium atom mean? It means that its velocity is on the order of a centimeter per second, converting its kind of velocity to kinetic energy and kinetic energy to temperature in the standard way. We then further cool them in magnetic fields and so forth using tricks that received the Nobel Prize in the 2000s, and we made what's known as a Bose-Einstein condensate, where each one of those rubidium atoms is in a trap, and they're all in the same quantum state. That quantum state is about 1 millimeter in size, and the velocity spread of the atoms now is measured in temperatures, measured in picokelvins, and it corresponds to velocities of just hundreds of microns per second. Then we take those atoms and we grab onto them with a beam of light, and we launch them along a ballistic trajectory where they go up that tube, they turn around, and they fall down that tube under the influence of gravity. Just as if I took a fistful of sand or a rock and I chucked it up in the air with a suitable velocity. For us, it was like 12 meters per second. It goes up, turns around, and comes back down. And because these atoms are cold, 10 picokelvin, their velocities are no more than about 100 microns per second. All million of them or so just kind of go up like this fistful of sand and then come right back down, and they're pretty much in the same place. Now, what do? As they're flying up the tube and coming back down, we hit them with pulses of laser light. And these pulses of laser light are designed to affect the operation of a beam splitter for de Broglie waves. Now, the atomic physics process is kind of subtle, but kind of what it does is if I have an atom in its ground state, and we're very good at producing the atoms in its ground electronic state, then when it hits this pulse of light, the atom, after a certain radiation interval, finds itself in two momentum states, separated by what we call two photon recoil momenta, the momentum associated with a single photon in the beam of light that we're irradiating the atom with. And these two momentum states are in quantum mechanical coherent superposition with respect to one another, which is to say that that same atom wave packet being the probability distribution for finding the atom, has two different momentum components. Well, that momentum difference is on the order of a centimeter a second. We have a way of amplifying up that momentum difference with more pulses of light, and at kind of time t equals 0 for this experiment, we have these two wave packets that separate in momentum by about 0.5 meter per second. So it's like I had a red marble and a blue marble, and the blue marble is moving 0.5 meter per second faster than the red marble. But those marbles are just two parts of the same wave packet for an atom. Those wave packets are then launched on this tower. It takes about 2.6 seconds for the wave packets to go up and come back down. They got different momenta. So as they're going up, they're spatially separating. And one part of the wave packet is drifting away from his brother with time. And by the time the wave packets reach the top of this tube, they're separated by 0.5 meter. Now, to bring them back together, I irradiate them with more pulses of light, and as they fall back, when they get back down to this region here, they overlap, and then I take a picture of them. And what I look for is to whether or not these wave packets are going to interfere. This is a picture that kind of describes what I just said in words. We like to draw these space-time diagrams, which plots the position of the center of a wave packet as that's on the y-axis there as a function of time on the x-axis. And they start off, I'm taking out the overall sag due to gravity, the fact that I'm going up and down underneath the gravitational field is subtracted off, and I'm just plotting the relative positions of the two wave packets. And what you see is the two wave packets are drifting apart as I irradiate the atoms with laser light, and they separate by this ½ meter before I bring them back together at a time 2t, which is about 2.6 seconds after I first launched them. And after that final pulse, we then take a look at the probability distribution of the atom waves and see what we find. So this is, again, false color processed data that shows us the distribution of atomic density in this region. And I'm showing you two sets of images. One where we adjust the pulses of light so that the wave packets separate by a centimeter, and another where we adjusted the pulses of light so they separate by 50 centimeters. And what I'm looking for, what we were looking for in this data was the following. If I have interference, what I expect to happen is the atomic populations, the probability for finding atoms at a given position in my detection region, I expect them to oscillate between two positions depending on the relative phase of the two sets of waves that are overlapping and interfering at the beam splitter. I could build an optical interferometer that was exactly analogous to this, and instead of talking about atoms interfering, what I would be asking the question is, when the light came back to the exit beam splitter, did it all go in this direction, or did it go to that direction? And did my detector over here light up, or did the detector over there light up? Now, the way the detector is lighting up is by seeing atoms in one of the ports or the other port. And quite remarkably, as I change the relative phase between the two paths, and what am I calling the two paths? I'm calling one path this upper path, and the other path this lower path, associated with the wave packets separating by ½ meter. As I change that phase, I see constructive and then destructive interference at the output ports of the interferometer, which is to say, when there's destructive interference, I see all the atoms at that position. When there's constructive interference, I see all the atoms at that position, just as you see constructive and destructive interference with any other wave. And so the signature we were excited to observe was that when we went to 54 centimeters, we were still able to see this oscillation in probability of detecting atoms in one port and the other port. And there are many non-basic physics reasons for why that might not happen. It's very easy to mess up this experiment. It turns, if you go through numbers and you ask, gee, what kind of stability do I need to have on the atom waves for them to come together and interfere constructively? It turns out that if you give them extra momentum or extra velocity of just about 10 nanometers per second, I should get my units right, 10 nanometers per second, which is much slower than an ant crawls, that these waves will no longer come together in a way that they interfere constructively. And we spent years getting our apparatus to a position where we observe interference over ½ meter. Now, if you're not in the field, you might think, ½ meters doesn't sound like much to me. Like we interfere, I was just talking with Lawrence, and we're talking about interfering microwaves over distances of, AU. So, what's up with ½ meter? And well, let me remind you that we're not talking about interfering photons. We're interfering rubidium atoms. These are chunks of matter. They're not quite a human being in two places at once, but they're chunks of matter that are complicated. Lots of protons and neutrons and electrons all running around in that grab bag, and all somehow, via the laws of physics, being allowed to be at two places at once. To put that number in a different context, what's the size of an atom? Size of an atom, on the order of an angstrom, ½ an angstrom. We're separating the atoms by ½ an angstrom, 10 to the minus 10 meters. We're separating them by almost a meter, 10 orders of magnitude larger distance than the size of the object itself. And you just ask the question, well, That does seem kind of amazing. How and why does nature let that happen? And can I learn something about the laws of nature by observing that interference? For example, these atoms are propagating through a gravitational field. We don't know. I mean, Newton told us that apples fall to the floor. But beyond that and some snippets of relativity, we don't know a heck of a lot about gravity in the structure of space and time. Or these atoms are propagating through space. But at the energy scales we're probing, what is the structure of space? Is it homogeneous and uniform? I mean, we like to think of that when you take your intro physics courses, you will happy to lay down rulers and have a clock that seems to tick completely uniform. But maybe it's fuzzy, maybe it's grainy. And maybe when you stick a quantum particle through space at the scales that we're now investigating, maybe it gets to the point where you might not expect to see these two sets of waves come back and interfere constructively. That's the motivation for doing this sort of experiment. So along those lines, my group is not the only group that's exploring quantum mechanics in this way. You could say, well, what are you testing? Well, one thing you could say you're testing is kind of macroscopicity. How big can I have an object? How far spatially separated? How massive can it be? How much time does it get separated? And then, before I come back and have it interfere? What are the limits that we as a community are placing on quantum mechanics in terms of allowing macroscopic phenomenon to be quantum? And so there's a great set of theory work out of the Vienna group. Nimrichter is the guy who did this. And this chart is, I'm not going to explain it in detail, but what he's doing is he's comparing all sorts of different experiments. People who interfere, the Vienna guys interfere buckyballs. There's another guy who interferes molecules that are getting pretty darn heavy. He makes them separate, be in two places at once, come back together and interfere. And he has a way of comparing all those different experiments and asking, how macroscopic, is quantum mechanics for this experiment. And the work we did in this test theory is shown by the green lines and is basically excluding a very large parameter space for, the correctness or incorrectness of quantum mechanics. And in some regions, by virtue of having just a lousy rubidium atom separated by a half meter, we're improving limits of our knowledge of quantum mechanics and macroscopicity by 4 orders of magnitude. This is a phenomenological theory. It's just a way of comparing numbers for different types of setups. And so you could ask, well, what kind of theories actually do erode interference? How might the physical world be broken? And this is where it gets interesting, and also we're entering the realm of not established science, and anybody will put up one of these theories, and someone else will shoot it down the next day, say that doesn't make sense because of this or that. So just to give you a flavor, so these models kind of proliferate on, I want to say a daily basis, but on a monthly basis. And I was amused to see this preprint that showed up on the archive server recently in the context of our work. The idea is that space is filled with a wormhole gas. It's like, and beyond uttering those words, I really don't know what they're talking about. But there's, and you can do some quantum physics that says that, well, these atoms come fly along, and they collide with these small wormholes, and they entangle themselves, which is our fancy way of saying they get a little momentum exchange and something more when they collide, and in such a way that you would never see interference in the experiment I just showed you. And this model is no longer taken seriously, but back in the late 80s, it was discussed in the context of the black hole entropy problem, and names like Hawking and Susskind are associated with this theory. They've since discredited it, but these guys came back and revived it, these authors, and showed that this kind of experiment we're doing constrains that. I just put this up as one example. There are possibly many, there are a lot of other theories. The ones I'm most interested in are the ones where we think about space-time as not being homogeneous and kind of Planck scale fluctuations giving a fuzz to it. And let's go do the experiment. So ultimately, I'm an experimental physicist, and I'm supposed to be blind to the theory, which is good because I don't understand most of that theory anyhow. And let's just do the experiment and see what nature tells us. So basically, I focused on the idea of, can I see any form of interference at all? Or do I completely erase wave-like behavior? And racing wave-like behavior would be a way of making quantum mechanics go away. But oftentimes, we build interferometers, and we accept that they work, and we use them as tools for metrology in the following sense. We measure the relative phase between the two arms of the interferometer. Once I know that I can have interference, then I can measure the relative phase of propagation of one interference path over the other interference path. And by measuring that so-called phase shift, I can learn about the environment that the probe particle, in my case atoms, registered. And so this is what got the field started in the early 90s. It was recognized that by building such de Broglie wave interferometers, you had an exceptional tool to measure inertial forces. Because as the atom wave packets are propagating through the gravitational field, for example, one of the wave packets sees a slightly different gravitational potential than the other. Its velocity changes in a different way. That leads to a phase shift, which leads to a change in the interference pattern. You measure that change in the interference pattern, you measure the phase shift, you measure the strength of the gravitational interaction, for example. This is a lot of equations just to show you that since the early 90s, we've been figuring out how to compute these phase shifts for this quantum mechanical system. And there's a bunch of jargon associated with them. What that basically amounts to is if I think of the atom as a wave, I count up the number of wiggles in that wave as it propagates from the first beam splitter in the interferometer to the exit beam splitter in the interferometer for both paths. And this is just the fancy mathematical way of saying that. And what you find is that what I just advertised, you have a fantastic sensitivity to detecting inertial forces. So fantastic, in fact, that there's a burgeoning industry now. This is a company I'm associated with, but now there are probably 5 companies worldwide that are all producing inertial sensors, gyroscopes, gravimeters, gravity gradiometers, based on this interference principle I just talked about. Now, these aren't 10-meter tall albatrosses that we're using to test basic science. These are compact devices. This is a compact gravimeter. This is about 5 years old now. And what this is designed to do is to measure the Earth's gravitational field. You take this and put it in a location, and you just walk away from it. And Earth's gravitational field changes in strength quite remarkably by about part in 10 to the 7 with time due to the motion of the sun and the moon. And for example, this is the kind of data you would get. It's very useful for geophysicists. Our interests are not commercial in the university. They're more like, if I build one of these giant scale interferometers, what kind of stuff can I measure? And so here's my last equation slide, I think. This is what we call affectionately as the term list, which is the output of a computer code that calculates analytically the phase shifts as a function of the sort of forces that are acting on the atoms as they're flying between the input and exit beam splitters. And I basically want to throw this up to show you a couple of the most interesting terms. This one here is the phase shift. So when I multiply k, which is the propagation vector of light, times the acceleration due to gravity, times the time it takes, the time that the atoms are separated, when I product all that stuff, that gives me a phase factor that relates the strength of the gravitational field to the fringe shift at the output port of the interferometer. And what's amazing is for this, that 10-meter tower I just showed you with the half-meter wave packet separation, that basically for 1 g's worth of acceleration, almost 10 to the 10 radians of phase, or 10 to the 9 cycles of phase, have evolved between the upper and lower trajectory. What does that mean? Let me put that number in context. If I can measure the phase shift, when I take a picture, I see a fringe. So I basically can measure that phase shift at least to 1 part in 10 to the 10. And then when we look at counting statistics, how many atoms I detect, we can split the fringe, as we say in spectroscopy, and we're able to resolve changes in G at the part per 10 to the minus 12 level, which is to say if G had changed the acceleration due to gravity by 10 to the minus 12, in principle, we would be able to observe that by seeing a shift in the output fringe of our interferometer. Just like you would when you're doing any other precision interferometry or metrology, observe correlate a fringe shift with some interaction. And so the question that, scratch your head, so, gee, 10 to the minus 12 that's pretty good sensitivity. What kind of things can we investigate? And so I want to tell you about an experiment that's currently underway on the next slide. But it's easy to throw around these orders of magnitude. 10 to the minus 12 of acceleration due to gravity. That is a tiny number. How small is that? Well, the gravitational attraction between two of you sitting next to each other is about 10 to the minus 9 of g. So 10 to the minus 12 is part of 1,000. It means if one of you guys drank a cup of coffee, that would change your weight by an amount that this detector, in principle, will be able to resolve. What are we doing with it? Well, there's lots of obscure theories that can be tested. I'll tell you about some of them, but this is maybe the least obscure of those. What we're doing is checking Einstein's theory of a GR and one of the core general relativity and one of the core tenets of that theory, the equivalence principle. We all know the equivalence principle. It says that it's the leaning tower of Pisa experiment. You drop the bowling ball and the feather, the rock and the feather, and if it's in vacuum, they're all going to fall due to laws of gravity at the same rate, or do they? And the question is there some sort of obscure beyond standard physics theory that makes it so stuff of different composition, material composition, falls at different rate? Well, the advanced version of that experiment is the following. We are taking two isotopes of rubidium. I can't show you the data yet. Rubidium-87 and rubidium-85. And we've loaded them into this tower. And we launch them up simultaneously. They go up and they come down all together. And then we apply the same set of pulses of light. And this pulse of light is engineered to simultaneously address both the rubidium-87s and the rubidium-85s in such a way to make completely identical interferometers, as identical as we think we can make them. Then at the output port of those interferometers, we take pictures of both the rubidium-87 and the rubidium-85. And if I go back to this slide, I have this leading phase shift here, which is independent of the mass or the isotopic composition of the atoms. And so I would expect to see the exact same phase shift for rubidium-87 and rubidium-85 if Einstein's principle of equivalence is true. So how good can we get? Well, by doing data averaging. Kind of typically when you design an experiment like this, you say, let's collect data for about a month. And after a month of data collection, we think we're going to be able to resolve differential accelerations at the part in 10 to the 15 level for one isotope versus another. Again, small number, I'm just throwing it around. If you're in this field, if you're familiar with some of the other work, there's some great work going up at the University of Washington testing these principles. The world record is kind of now at the part in 10 to the minus 13 level. And there's a lot of interest in pushing that number deeper. Some theorists want to get to the 10 to the minus 18 level. And their theory is they say that's an interesting level because there are new particles flying around. They call them moduli particles that would break the equivalence principle at this level. You might say, and this is a conundrum you get when you're doing this kind of precision measurement type stuff, what's the point? You're talking about 15, 18 digits. Who the heck cares? And certainly I don't care for building instruments to measure Earth's gravitational field or build gyroscopes for aircraft and so forth. But if you say, I really care deeply about understanding the structure of our universe, our cosmos, then you care about this. If this is a path to discovery of new particles, then I care about it. And again, I'm not the guy who can say this for sure is a path that it's not like the Higgs boson. So if I get 10 to the minus 18, I'll see a new particle. But there are a lot of people out there who are interested in knowing whether the equivalence principle is actually solid at that level. So, and we hope to be setting some of the tightest limits and also doing it in a different way from the other experiments with this kind of neat quantum interference approach. We've been building towards this experiment for about a decade, and we are now delighted to be getting some of our first data in. And this is what the data looks like. I don't have a number to quote, and I don't know if that's really even the right thing to talk about right now. But what I'm looking at is the cloud of rubidium-87 and the cloud of rubidium-85 after they've simultaneously exited that final beam splitter. I'm taking a picture of what those clouds look like as they interfere, and we've purposely manipulated these wavefronts so that when they interfere, I see a kind of a correlation across the probability distribution. This is for one of the atomic states that's part of the interferometer, and this is the other exit port of the interferometer. So this is like if I built an optical interferometer having a photodetector at this port and this port simultaneously and slightly misaligning it for the interferometry experts to see these, to reveal the phase of the interference fringe. And what I'm interested in doing is comparing the phase of the interference fringe, say this one here, to the phase for rubidium-85 and making a precise measurement of that. And we're delighted to see that we're measuring the relative phases now, and we're accumulating statistics. We're doing this in a way that's blind, so I'm not willing to go and tell you, oh, I think my data's good right now. I have to do a lot of systematic checks, and then after I've done all of that, we do what they say, take the number out of the box, and I tell you if I think the equivalence principle is valid or not. So another way of looking at this, we say, who cares about the equivalence principle? One more time, why do I care about the equivalence principle? And why do theorists get excited about this kind of work? And as you know, cosmology has got a couple puzzles right now. And one of them is, we know that there's stuff out there, dark matter, but we don't know what it is. And so everybody's trying to build, this is my experimentalist perspective, a detector for dark matter. And you might ask the question, well, can equivalence principle measurement be a way of looking for dark matter? And it turns out that there's some recent theory that puts this on a fairly firm foundation. The point of this chart is just to say that for a pretty popular model of dark matter, checking for violation of the equivalence principle is tantamount to identifying the presence of this dark matter and the sort of mechanisms that would break the equivalence principle. And this is the kind of theory that supports the experiments that we're doing. Let's see, I want to kind of spend the last few minutes talking about another kind of what I think is an exciting frontier for pushing this sort of precision measurement. I say we're building great accelerometers. Well, this great accelerometer is great at measuring very tiny accelerations. What is a very tiny acceleration of great interest to the scientific community? That's the acceleration due to the gravitational waves. And one of the greatest results, probably, different physicists have different ways of expressing this hyperbole, but the last 10 years, the last half century is our recent observation as a scientific community of gravitational waves due to black hole in spiral. And I have a slide here showing what's going to be the iconic data from the LIGO collaboration, where they have detected a gravitational wave that has, from this black hole merger, stretched and contracted space-time here in the US between two distant locations, one antenna here and one antenna there. And what's happening as this gravitational wave is propagating through the antennas is it's literally introducing accelerations on the test masses that comprise this interferometer that are registered by doing precision optical interferometry. And by looking at the positions between those test masses, you can infer the presence of a gravitational wave. And this is the gravitational wave flying through one of the detectors. So scientific community has had that data for a number of months now, and people have been chewing on it. And one of the interesting things to note is if you take that event, which is known as GW 150914 after the date of discovery, the LIGO detector was tuned up in this region. This is the frequency of the gravitational radiation, and this is basically the amount it's stretching space and time, or the acceleration it's introducing on the test mass. And you say, well, what did that gravitational wave look like before it hit the sensitivity window of the LIGO detector? And that's Sasana and colleagues put this on the archive recently. You kind of can back extrapolate that in spiral to earlier epochs. And so before the black holes finally merge, what does this look like? And you find this really interesting region in low frequencies final merger was at hundreds of hertz, and when you go back before that merger happened, frequencies of a hertz or 10 to the minus 1 hertz, and ask, what's this associated strain of these black holes as they're doing this before they come in and merge? That turns out to be a strain level that may be detectable by different sort of detector. When we do optical astronomy now, we have different telescopes to look at the cosmos. It's not like there's one telescope that we look at everything. And so people that are interested in detecting these strains are now thinking about ways of building different telescopes to detect gravitational waves of different character. Well, we're interested in this region right here. These strain curves, these black lines are associated with a proposed space-based antenna, which is looking like it's going to be built. It will fly in 2034, and it'll be very good at detecting low-frequency gravitational waves. It'd be interesting to see gravitational waves in that region of the spectrum. And that's where we think the atom interferometer may have a role to play. What we have in mind is taking what I've just shown you and putting them on satellites. And one satellite, I have one giant interferometer. Another satellite, I have another interferometer. In both cases, I have the wave packets separating and recombining by a half a meter to a meter. And then I compare the phases at those two outputs using an optical field, which I propagate between the two satellites. This is my theory colleagues will describe that instrument with the following space-time diagram. And basically, this is one interferometer, this is another interferometer, measuring the phases on the outputs simultaneously. By comparing the phases, if a gravitational wave rolls through, the phases will jitter back and forth. And by looking at the jitter in those phases, I can make an inference about the strength of the gravitational wave. So it's kind of like that equivalence principle measurement, except now I'm not comparing the acceleration of 85 and 87. I'm comparing the acceleration of one ensemble of 87 here and one ensemble of 87 there. And when I say here and there, I want to separate those interferometers by 10 to the 7 to 10 to the 8 meters. And this is the kind of, so I can only do that in space. And then if gravitational wave rolls through, we have a way, we think, of detecting them. So how sensitive can it be? This is kind of a gravitational wave detection expert plot, but one of the things you care about is the strain sensitivity in 1 second or per root hertz as a function of the frequency of the wave. And this is the kind of sensitivity we believe we can achieve, which is orders of magnitude below what other sensing methodologies can give right now. And so we're just kind of doing the theory and the experimental work as part of how I view the equivalence principle work that we're doing now to support the design and construction of a prototype antenna along these lines. And the Keck Foundation is funding us to do that. One more theory slide here. I mean, we're not just interested in black holes. In fact, the theory of inflation says that as the universe went through the inflationary epoch, you freeze into space-time gravitational waves, so-called stochastic gravitational waves, kind of rumblings, little stretchings and contractions of space-time that they're everywhere around us, but they're at such a small amplitude that we basically never see them unless we spend the resources to build this type of antenna. A lot of people are interested in trying to figure out how to detect those so-called stochastic fluctuations, how to build an antenna sensitive enough to do this. The people who do optical interferometry have conceived of this apparatus called the Big Bang Observatory, and this is our atomic physics counterpart. And this chart basically says this is a sensitivity curve we think we can achieve with our apparatus, and it says that we think we can get to a point where we test some of the pretty widely accepted models for inflationary cosmology. And this will be my concluding slide. You might say, well, that's all very well and good, but those gravitational waves are interesting. They're going to teach us a lot about the universe, but is there something a little bit more practical we can do? And so this same kind of differential accelerometer geometry that I just described for wave detection and equivalence principle also turns out to be a very good way of just detecting gradients in the Earth's gravitational field. And so with NASA funding now to Eosense, we're building a gravity gradiometer, which is going to have two clouds of atoms separated by about a meter, detecting changes in the acceleration due to gravity between one location and the next. And why would you want to do that? Well, by orbiting the satellite in low Earth orbit, many times over the various continents, you can measure small ripples in the Earth's gravitational field. This is a map that's been produced at NASA Goddard by Scott Lutke, and it basically shows you how you can infer from gravitational gradient measurements mass distribution measurements. And that's of great interest right now because that, what's informing that mass distribution is like the water table or the melting of the glaciers in Greenland. And so precision time-dependent measurements of this is thought to be very important for climate science. And so we're building the prototype instrument that we call the CAGG. And if things go well, it may be a viable candidate for the follow-on to the GRACE mission, which was used to acquire that information. At this point, I want to stop and thank you for your attention.
Great, thank you. I love this stuff. So if you have questions, please wait for the mic so that we get this all recorded.
Thank you. About 3 slides back, you had a sensitivity plot that had a Q factor on it. Could you explain what the Q factor relates to?
Let's see, so that is right here. So we've been making proposals for these detectors for a number of years now, and as time has gone on, our creativity has also enhanced, we think. And so what the Q factor is associated with a space-time diagram that looks like this. The left is one interferometer, the right is the other interferometer, and what we're making the wave packets do in those interferometers is oscillate back and forth like a resonant detector. And if they oscillate at the same frequency as the gravitational wave coming in, then we get a kind of a resonant enhancement of the phase shift, which really gives us a dramatic improvement in the sensitivity to the gravitational wave. And the Q is telling us basically how many oscillations there are. Thanks for that question.
Over here. Hello. Hi. When you talk about macroscopic quantum effects, I think some other groups have been looking at taking like micron scale oscillators and trying to cool them into their ground states. Yes. So could you contrast how that tells you about macroscopic quantum compared to what you've talked about here?
Wonderful, wonderful. So that is the, let me go back to slide earlier in the talk. That was this one here. If I can get it. So that's exactly the question that Nim Richter and his colleagues at Vienna were trying to address. Because they seem, what we're doing with atoms is very different from cooling kind of a micron-sized object into its ground state. Yet they're both somehow testing quantum mechanics. And so is there a way of comparing, which one is, the constraints that each one of these experiments is placing on quantum mechanics? And so there's this figure of merit that was invented by Nim Richter and Hornberger, quote, macroscopicity, that is designed to exactly compare that situation with the situation of the atom wave packets. And certain assumptions have to be made. Like you have to decide, do I really care about mass, or in the test? Do I care about the spatial separation? And those are all things that get fed into these theories, and or Nim Richter's theory, and he tries to tell us what to care about, and then gives us this way of looking at them. And so it turns out that the experiments that you described, although they have great promise in the future and are really exciting. I mean, another part of my group is trying to do kind of experiments like that. But right now we're just starting to learn how to crawl with those experiments. And I hope someday we will be having beads that are separated by millimeters, and then come back and interfere. But we're nowhere near that yet.
Hi, that was a really great talk. Thank you for that. Capital G, Newton's gravitational constant, is probably the most poorly constrained fundamental constant of the universe.
Yeah.
Do you know of any experimental designs using interferometry to better constrain that parameter?
Yeah. So that is, and I didn't talk about an experiment to look at capital G, but that's certainly something we do with this apparatus. And in fact, After our equivalence principle experiment, that's the next one on the books. I think I'll be getting there in about a year and a half. We did a preliminary measurement back in 2007 where we measured capital G to about a part per thousand. A little context, right now there are lots of people who measure capital G, and we've been doing that for a long time, and their error bars are small, 10 parts per million, and yet they don't agree at kind of the 100 parts per million to part per thousand level. It's an embarrassment. And there's been all sorts of speculation recently of kind of mechanisms that non-standard physics that may be responsible for the diversity of measurements we say. Maybe there's something, one guy recently, there's a paper out that says, oh, capital G oscillates in time, and at the 100 part per million level. Other people say, well, the guys who are doing those measurements, which involve, you have to be a real believer in classical mechanics and the properties of torsion pendula. They say, well, we don't really understand how those torsion pendula work, and these guys who did those experiments don't really know what they're doing. And so, our perspective is we're just going to go and use this quantum mechanical method and see if we, see what we observe. So there is physics associated with that, and people have tested, why measure capital G? Well, there might be theories that make it other than what we think it should be. There's also one of my colleagues who did some of the best measurements in the 90s and 2000s in this area says the reason you measure Newton's constant capital G, kind of when you look at the equations and what depends on it, oftentimes capital G drops out, and so it's like the world's most uninteresting fundamental constant. So the reason you do that as experimentalist is because it's like doing push-ups. It makes you stronger. You get stronger if you do other experiments. So I don't know. I don't quite view it that way. I think there is something there, and yeah, that's something we're actively engaged in. Thanks.
Over here. Hi. This is, you have to forgive me, this is kind of a theoretical question, but it's pretty straightforward, so hopefully it won't be too scary. I mean, looking at this chart, you got rubidium's pretty big, and some of this other things like the molecules from 2013 are pretty big, and you're making interference patterns out of them. Now, I'm made out of molecules, and much to the chagrin of my wife and kids, I can't be in two places at once. So there's got to be a boundary in there, and what is it? Why is it where it is? How does it work? I mean, and what does it even mean for a molecule to be in two places at once? I mean, I'm still kind of trying to figure out why electrons can be in two places at once, but like a whole molecule is an order of magnitude more counterintuitive to me than an electron.
Yeah, I can't answer your question. I mean, that's why we're doing the work. An atom, can you imagine an atom being half of the popular press we got when we published was amusing, and some of the questions we got were like, okay, if you could do an atom, if you can do molecules, then as you say, you're made up of molecules, then maybe you can envision the day when something more macroscopic is in two places at once, and you can build the quantum teleporter. And I've got investors ready for you. And I'm like, it's like, well, we're not ready to go there yet. And to me, it's just fascinating how big can we go? And so data that I didn't have a chance to tell you about, but is kind of in that direction, is what we're doing now is we're taking individual atoms and we're entangling them, correlating them in clusters of about 1,000. And so not a single atom, but now kind of molecules that are 1,000 atoms in size, and we're going to see if we can separate them by a half meter and if we still see interference. I think it's just a stepping stone. I have no idea whether human beings will ultimately be able to do that. If you believe the fundamental laws of quantum mechanics, it's all about controlling the environment. The reason why we don't think we see human beings interfering right now is because there's stuff that collides with you that collapses your wave function, and we all are supposed to be somewhat comfortable with that as erasing interference. But the basic laws say that should be able to happen if I control the environment well enough, and let's see.
My question has nothing to do with your talk, which was great, but with the background. You were introduced, mentioned that quantum mechanics has been demonstrated to work from the Planck distance all the way up to Bose-Einstein condensates. Mm-hmm. But what evidence? I mean, I know there's a lot of theoretical evidence, but where's the physical evidence that it works down to the 10 to the minus 33?
Yeah, so I think that's it depends. That's a statement that I would say is, I wouldn't say is on a firm foundation. In fact, there's experiment in way at Fermilab right now that's experimentally, it's called the holometer, and Craig Hogan is doing that, where he has there's some theory that says that as light propagates, you should see the influence of Planck scale fluctuations on the light. I think theoretically, a lot of people believe that quantum mechanics is working down at the Planck scale. And people have difficulty envisioning the universe where that's not the case. But experimental evidence at the Planck scale, I don't think is really there yet.
Yeah, it's string theory is, well, I go for loop quantum gravity before string theory for that very reason, that there isn't any experimental verification at the string theory level. I just want to point out too that you can do a double slit experiment with an amoeba, but it will take 3 years because of the uncertainty principle. So nobody's done that yet. If you wanted to do it with a human, it would take you probably the age of the universe.
Well, okay, that's.
Do you want to finish?
Yeah,
with
so
comments?
I'd be curious as to why you say that.
Okay, we're going to powwow at lunch.
Yeah,
So, but I want to thank Mark again. Should we all thank him again? That was a really great talk.
Thank you very much.
Really great. And I want to give him a SETI mug, which has 2 communicating robots, a la Asimov-looking robots.
Awesome, thank you. This will be my
Thank you
coffee
very
mug
much.
tomorrow. Yeah, thanks.